Hi everyone, now we are going to study the Poisson process. We have previously introduced this process, but we need to cover it in a bit more detail because it plays a fundamental role in the study of jump processes and also in the characterization of the Levy processes, which is a more general process that encompasses both the Brownian motion and the Poisson processes. Understanding of Levy processes will enable us to introduce more sophisticated stochastic processes and hence up the game a notch. Previously, in the introduction video, we gave the definition of Poisson process, pretty much mimicking the definition of Wiener process, except that the increments have Poisson distribution as opposed to normal distribution for the Brownian. So a Poisson process starts at 0 with probability 1 and has independent increments which follow Poisson distribution. So the increment distribution here determines the number of jumps over the interval, with lambda determining the intensity of the jumps. Higher lambda means more jumps. Notice it's implied that the increments are stationary because they depend on the length of the interval, t minus s, and not the absolute value of t. Now this definition gives us enough to characterize the process, but there are several alternative characterizations of the Poisson process which provide more insights into the process and also how this Poisson density comes about. So let's start from the beginning. Let's consider a time interval. Assume some event or arrival process, such as the arrival of customers at the bank branch or arrival of telephone calls at a call center. Assume we start at time 0 and let's represent the waiting time to the first arrival by x1, the waiting time between the first and the second arrivals by x2, the time between the second and the third arrivals by x3, and so on. We assume these xi's are independent, so you're not visiting banks with friends and family. They don't need to know the balance of your account maybe, and Kim Kardashian is not in the queue either. You know the independence of arrivals assumption is not going to stand a chance with Kim and her followers. Let's represent the arrival times of these events by capital T's. So T0 is the time we start observing the process, T1 is the arrival time of the first event, T2 of the second, and so on. So T0 equals 0, T1 is then the time from 0 to the first event, which is the same as x1. T2 is the time from 0 to the second event, so it is equal to the sum of x1 and x2. T3 is the time of the third event, so it is the sum of x1, x2, and x3, and so on. So we can write Tn, which is the time from 0 to the arrival of the nth event, as the sum of the waiting times between these events. Now the Poisson process is just about keeping count of these arrivals, so it is essentially a counting process, representing the value of the Poisson process over time as nt. We can easily write its value in terms of the capital T's. So to determine its value at small t, you count the number of arrivals before time t, which you can do by extracting all the capital T's, which are smaller than or equal to t, and then the maximum index value is the number of events before time t. You can also write this in terms of x by replacing Tn by the summation of x's. So the process value jumps by 1 at each arrival. Let's work with the process to befriend it. Let's start at time 0. There is no arrival until t1, so the counter stays at 0. We get an event at t1, so the process jumps and then stays at 1 until the next arrival, when it jumps by 1 again, and so on. This path is an example of one realization of the random process, so the times of jumps is stochastic and will vary according to some probability distribution that we're going to study in detail. Looking at the path, we can see the paths of the process are not fully continuous, but they are continuous in a different sense. We have no issue with the continuity between the jumps as we have a straight line. At the jump time, notice the process has limits from both sides. For example, approaching the jump time from the left side, we see the limiting value is the value of the process just before the jump. Remember, the process doesn't have to attain the limiting value for the limit to be defined. This is basic calculus. But the process is not continuous from left due to the jump. From the right hand side, the process has a limit, but is also continuous because the process attains the limiting value. So the process is right continuous with left limits, abbreviated as RCLL, or what's written on the screen in French, and abbreviated as cadlag in the literature. Essentially, this cadlag specification is a way to ensure that the jumps are non-anticipative. One could have alternatively defined the jump process as left continuous with right limits. So essentially the fill and unfilled circles would have swapped positions, but then the jumps would have been anticipative, which is not what we want for a random process, though this alternative definition is more suited for the specification of trading strategies where we decide our holdings in advance. In other words, the holdings are predictable and these rules are arbitrage. Now the axes are independent variables, so the next realization will produce different t's, and hence the jumps time will vary from one realization to the next, but this is what probabilities are for. So let's discuss probabilities. Let's say the value of the process at time t is equal to j. Now this is a stochastic process, so we should really be talking about the probability of the process taking the value j at time t. Now consider a small time step, delta t. Three things can happen before the next observation, so we have three branches. One event occurs and the process value increases by 1 to j plus 1. More than one event happens and the process value increases to more than j plus 1, or no event happens and the value stays the same. Now consider the probability of the first branch. This is the probability of j increasing by 1 during a small time interval of length delta t, conditional on the number of events at time t. Assume the intensity of the process is equal to lambda. We would expect that the probability that the process jumps over a small interval delta t is lambda times the length of the interval. The O of delta t means the residual will be of order delta t, which means the residual term will go to 0 faster than delta t. So as we let delta t goes to 0, this thing will go to 0. For example, delta t squared goes to 0 faster than delta t as delta t becomes smaller, whereas delta t itself goes to 0 at the same rate as delta t, so it is not O delta t. And as delta t is assumed to be very small, we expect the probability of the next branch, which is 2 or more arrivals, to be negligible, which again is captured by O of delta t. And as the total probability equals 1, it's easy to infer that the probability of no jump over a small interval is equal to 1 minus lambda times the length of the interval, and we will have the O delta t. This is very similar to what we saw in the SIR model, by the way. After all, both are counting processes, number of people and number of events, so we won't expect them to be much different, though the structure here is much simpler because we are tracking just one variable. There we had two, remember, susceptibles and infectives, and we shall be able to solve the resulting Kolmogorov or master equation here as well. So we shall see the link between the Kolmogorov equation and a probability function more clearly. So we shall see that solving the Kolmogorov differential equation gives us a probability distribution, so we can see that the Kolmogorov is essentially another way of describing the probability. Now back to our tree. Let's see it from the other side. Say we want to determine the probability that the value of the process at time t plus delta t equals j. We can follow the logic we applied to the tree and reverse order. So it might be that the process value was j minus 1 at time t, and one event occurred during the small time interval delta t, or there were fewer than j minus 1 events by time t, and more than one event occurred during this small time interval, or finally nothing happened during the small time interval. Now we need to change the conditional probabilities to reflect the new perspective. So for the first branch, we will just need to replace j by j minus 1. We can ignore the second branch because the probability is of order delta t, so it is going to vanish in the limit anyway, so no point in wasting any time on it. And for the final node, it's good as it is, so we don't have to do anything. And as we mentioned before, the probabilities take the simpler form because these are just probabilities of changes in the value of the process over an infinitesimal period. Infinitesimal means infinitely small, and this is very much like retaining just the first term of the Taylor series expansion, and we know the first term in the Taylor expansion will provide sufficiently accurate estimate if the approximation interval is kept very small. Now to chain or link the probabilities of the process value at time t plus delta t to the probabilities of the process value at time t, we just recall the Chapman-Kolmogorov equation. As we know, this combination of the British and Russian names represents a very simple concept. All it is saying is the probability of the process value increasing from some initial value at time 0 to j at time t plus delta t is equal to the probability of the process value going from the initial value at time 0 to some intermediate value at time t, and then from the intermediate value at time t to j at time t plus delta t, summed across all possible paths. As the time interval between the intermediate point and the final point is very small, we only need to worry about the two possible paths, the value increasing by 1 or staying the same. The probability of any other path over a small interval is negligible or order delta t, as we discussed before. Now the standard way one writes this probability is as follows. It really is a succinct representation for the probability of the process taking value j at time t. We have 3 of them here, so let's replace them one by one. On the right hand side, they have the same t, but different values for j. There's j minus 1 and j. And on the left hand side, we have just j, but the time is t plus delta t. So let's make the replacements. Let's gather the O of delta t terms. The probabilities multiplied by order of delta t will give an expression of order delta t, so this is all legit. Now let's get rid of the brackets. Now if we shift this p to the left hand side and divide through by delta t, and then let delta t goes to 0, the expression on the left hand side turns into derivative, and the last term becomes 0 because a term of order delta t goes to 0 faster than delta t by definition. So what we got here is the Kolmogorov forward equation or the master equation. Here it is a differential difference equation. Differential because we have the derivative term, and difference because we have the lagged value of p. The equation is indexed by j, so it means it actually represents a system of differential difference equations. We know j, which is the number of events, could be any integer, so let's enumerate the sequence. If you plug in j equal to 0, then the first term on the right hand side will be 0 because probability of negative number of events is 0, and in the last term we just replace j by 0. And if we plug in j equal to 1, then j minus 1 will give 0, and j is obviously 1, and so on. For a generic index n, we just get n minus 1 in the first term on the right hand side and n in the second term. Now this system of equation can be easily represented in terms of matrices. The right hand side can be written as the product of a matrix and a vector. We can easily verify this by just carrying out the multiplication. So the differential difference equation in terms of matrices can be written as follows, and you recognize this equation as the Kolmogorov forward equation or master equation if you are from natural sciences. This is pretty much a matrix form for the differential equations, which enable us to write the differential equation in matrix form. The previous version shows a generic element j, and this matrix form captures the same thing across all values of j. The matrix Q is the infinitesimal generator. This infinitesimal generator is quite easy to explain, by the way. We know that in a small time interval, the process value can stay the same or increase by 1. So assume the process value is 2 minus lambda reflects the loss of probability mass to the next value, and the plus lambda represents the gain from the previous value. Essentially, as an element of an increasing counter, you can lose to the next value, but then by the same token, you can gain from the previous value. We can solve these equations iteratively. The first row is slightly different because the process starts with nothing, or 0 to be precise, so there's no negative value, so that's why 0 is on its own. And the rest of the rows are similar. You just increment the index by 1 and you get the next row. So we can do with just one copy of this generic equation. We need the initial conditions. We know the process starts at 0 with probability 1. So the initial condition for the first equation is P0 equals 1. And by the same logic then, the process can't take a value other than 0 at time 0. So for j greater than 0, the condition is Pj equals 0. Essentially, we are saying that the process starts at 0. So the probability of the process taking value 0 at time 0 is equal to 1. And the probability of the process taking any other value at time 0 is then 0 by the same logic. Let's shift the Pj to the left hand side. Now we have solved similar equations before. The first one can be solved by straightforward integration, and the second one by the integrating factor method, which is the method we have encountered so many times before, but let's go through the motions. To solve the first equation, let's separate p on the left hand side. Now the left hand side is just the differential of log of p. Now integrate from 0 to t. So the integral and differential on the left hand side cancel, and lambda is constant, so the right hand side is easy. Now we can shift p0 to the right hand side and then exponentiate. So the log terms lose their logs as exponential and logs are inverse of each other, and the other terms gets exponential. Now we know from the initial condition that P0 takes value 1 at time 0, so we have the solution. What's this telling us, by the way? Well, the process starts at 0, so the probability of the process taking value of 0 at time 0 is 1, which is the initial condition. Now what's the probability that the process will continue to be 0 at a later time t, meaning there's no jump in time t. So as t increases, the probability of the jump increases, meaning the probability of the process staying at its current value declines exponentially. So that's the meaning of the solution of the first differential. Now let's move to the second equation. We will need to solve it for all values of j. So let's go iteratively, starting with j equal to 1. We can substitute for 0 from the previous solution we determined. Now we just have p1 to worry about, so it is just a first order linear differential equation. And yes, we recognize that this equation can be solved using the integrating factor method. The integrating factor is the exponential of the integral of the coefficient of p1. So we multiply both sides by this integrating factor. And the benefit of this multiplication is obvious, as we can combine the two terms inside one derivative. So it is the product rule of differentiation, but applied in reverse order. We can shift dt to the right hand side and integrate. So the integral and differential cancel. And we know from the initial condition that P0 is equal to 0. So we have solved for the probability of the process taking value 1 at time t. And we can now move to j equal to 2. So we just replace 1 by 2. As the steps for solving this equation for j equal to 2 are identical, we will just replace 1 by 2 everywhere. So starting with the first line involving p1, we replace j by 2. We do the same in the second line, and we can also substitute for p1 the solution we just determined. The integrating factor remains unchanged, so we just replace p1 by p2, where we combine the lambdas on the right hand side as well, and we can make the replacements in the next line as well. And we can now integrate. Notice integral of t is equal to t squared divided by 2, and we know p2 naught is equal to 0. So shifting the exponential term to the right hand side, we get the probability of the process taking value up to at time t. We can rearrange the terms with the view to generalizing the formula. Now let's repeat the process for j equal to 3. So we replace 1 by 3. We can substitute for p2 from the previous solution. The integrating factor remains unchanged, so we just replace p1 by p3 and combine the lambda terms. We can make the replacements in the next equation. And we know from the previous iterations the solution will just be the integral of the term on the right hand side times exponential of minus lambda times t. And notice integral of t squared is equal to t3 divided by 3, which we can rearrange. We can now see the pattern, so it is easy to infer that the solution for the probability of the process taking a generic value n will look as follows, and which we recognize as the density of Poisson random variable. We have the solution, but it's worth mentioning you can also solve this system via the probability generating function, and you can also approach this problem via Laplace transform. Depending on the time you're watching this video, you might see a link at the top right to a short video which details this alternative approach. Now we have arrived at the Poisson process via an alternative route, and we can use the building blocks that got us here to provide an alternative definition or characterization of a Poisson process, which goes as follows. Poisson process with intensity lambda is a process which starts at 0 and has independent increments, and the probability of one jump over a small time interval is lambda times delta t, and the probability of more than one jump over a small interval is negligible, or of order delta t to be precise. We can also write these in the abbreviated form. And let's bring back the previous definition so that we can compare and contrast. So the Poisson distribution and the definition can be replaced by the two conditions on the probability of jumps over a small time interval. Not too surprising, I hope, as you can view the definition on the left hand side as the infinitesimal or differential version. The Poisson process arises very naturally, so more characterization are possible. Let's discuss a couple more because these provide further insights into the dynamics of the process. Remember, we introduced the Poisson process as counting the number of arrivals over time. Let's reproduce the diagram. So the xi's are the waiting times between arrivals, which are independently distributed, and the ti's are the arrival times. So the arrival time of the nth event is the sum of the n waiting times. Now, can we deduce the distributions of x's and t's? If we can, then this might provide us with an alternative definition of Poisson process. Actually, deducing the distribution of x's is quite easy given what we have derived so far. Let's start with x1. We know if x1 were to be greater than some time t, it means the first event will not have occurred until time t. So this event represents the same thing as nt equals to 0. Let's take probabilities of both sides. Now we can write the probability expression in the abbreviated form. And remember, we determined this p0 earlier by solving the differential equation. Now probability of x1 less than or equal to t will be equal to 1 minus this probability, which we recognize as the distribution function of the exponential distribution. So we conclude x1, which is the waiting time to the first event, follows exponential distribution with parameter lambda. Now let's determine the distribution of the waiting time to the second event given the arrival of the first event at t1. So x2 greater than t, condition on x1, means that the counter doesn't change over the interval t. We can take probabilities of both sides, and because the increments of the Poisson process over disjoint intervals are independent, we can ignore the conditioning on the right hand side. And because the process is stationary, the probability depends on the length of the interval and not time, so we can ignore t1, and we can calculate the probability of Poisson process taking value of 0 at time t by substituting 0 in the probability density at the top right. And now we can repeat the steps on the left hand side to say that x2 conditional on the first arrival is also exponentially distributed. You can continue this process, or we can conclude that the waiting times are exponentially distributed, and we thus have an alternative definition of Poisson process. Before stating the definition, recall from basic statistics that the sum of exponential distribution follows gamma distribution, so the t's, which are the arrival times, will be gamma distributed. We can write the Poisson process in terms of axes by replacing t by the sum of axes, so it is easy to relate to the new definition which we are about to outline. So Poisson process starts at 0. The waiting times between the jumps are independent, and the waiting times follow an exponential distribution. So this is an alternative characterization in terms of the distribution of the waiting times. And let's put the three definitions we have discussed so far side by side so that we can compare and contrast. The differences are highlighted in green. Now we also know that exponential distribution can be approximating using Bernoulli trial, and the Poisson distribution can also be derived as the limit of the binomial distribution. So we smell an alternative definition can be given in terms of coin tossing. Let's consider a time interval from 0 to t, and let's divide this interval into n intervals of size delta t, which we represent by h for brevity. So we partition the interval into small sub-intervals. The first partition point is h, the second 2h, and so on until the last partition point n-1 times h. A different partition will produce different variables, and we will be interested in the limit as n becomes large, so that's why we need the n there. Let's associate with each interval a random variable z, where the first index captures the variable number and the second index captures the number of n sub-intervals that we use to partition the interval from 0 to t. So each of the x takes value of 1 with probability p, and value of 0 with probability 1 minus p. Given the Poisson process will have jump rate of lambda per unit time, so we set p equal to lambda times t divided by n. Now if we make n very large, then the probability of a jump in each of the sub-intervals will be very small, and we can assume that the probability of more than one jump is negligible. So the sum of the z's will represent the number of jumps, and we can thus represent the number of jumps as follows. Now the sum of Bernoulli random variables follow binomial distribution, so we can calculate this probability using the binomial density formula. We can write the combinatorial in terms of factorials. We can expand the factorial in the numerator so as to get the n minus n factorial term, which then cancels the same term in the denominator. So our binomial density becomes, now we can substitute for p. We can split the n minus n terms in the last power. Now we can take the limit. The first term will go to 1, but it might not be obvious, so let's rearrange the terms. There are small n terms in the numerator, so we can allocate 1n in the denominator to each of these terms. We can cancel the n's where we can. And now it's easy to see that this term goes to 1 as n becomes very large. So this term goes to 1, and by the same logic the last term also goes to 1. So we get, and now the limit of the last term is just how one defines the exponential. Remember our friend Euler. So we get the Poisson probability. So we have yet another definition of Poisson process in terms of Bernoulli trials. Actually, we saw something very similar in the Introduction to Stochastic Processes video. Remember, Lucy had a friend who could spin the coin really quickly. So you have seen the demonstration of the fourth definition of Poisson process. There's one further characterization of the Poisson process which is very insightful, but we will delay it to a sequel, and we will then discuss some important properties of the Poisson process, some of which will facilitate the transition to Levy processes. So I hope you enjoyed the video, and I look forward to seeing you in the next.